we can directly start. And
Yeah, let me see if I can move the screen somehow. Uh, is this okay?
yes, we can see it. That's perfect.
Okay.
Great. So in this case, I can introduce James Zhang from the University of Washington, who will be talking about valuations and applications.
So, thank you very much, Maximum. So first, I would like to thank the event for invitation and organizing. Um, so this is a non-associative algebra day, but part of my talk will be on associative algebra. Okay. Thank you, Ivan, for again for invitation and organizing. So I will start with some open questions in associative algebra or division algebras. Then I will talk about the connection between Poisson algebra, commutative algebra, and non-commutative algebra. Then I will focus on the Poisson side and talk about what is a Poisson valuation, give some definition. Then hopefully I have time to talk a few applications of this Poisson valuation. So that's my plan. So let's start with two open questions. Again, so these are on the associative algebra side. Eventually, I will move on Poisson side. These are kind of there's a non-associative structure, but at least on this page, all algebras are associative algebra. So here are two open questions. The first involves a Val skew field. So the first Val algebra, I mean, this famous first Val algebra is defined by generated by two elements, x and y, subject one relation, yx minus xy equal to 1. So this obviously this is non-commutative algebra. And we can show that the Val algebra is all domain. So we can take all localization. Then the all localization is a division algebra, or we call it skew field. So this skew field has been studied by many people. And here is one still open question. The claim said that every non-commutative sub-skew field of this Val skew field is isomorphic to itself, which is a Val skew field. Now, if we only consider skew field, including commutative ones, then of course commutative ones will not isomorph to Val skew field. But every non-commutative sub-skew field of this Val skew field seems to be isomorphic to the Val skew field. So this is the first open question. Okay. The second open question involves another skew field, which comes from the skew polynomial ring. So starting with a scalar non-zero scalar q, let's say q is not a root of unity, then we can define a skew polynomial ring, k qxy, I call it, which is generated by x and y, subject one relation, which is yx equal to qxy. Now, of course, if q is 1, this is commutative, but we are considering the case when q is not a 1, not even a root of 1. So there is a typo here, but q is not. Oh, this should be not root of 1, root of unity. So again, the same idea. This is all domain, so we can take a localization, and localization is a division algebra or the skew field. So now the question is every non-commutative subscale field of this Q skew field is isomorphic to the same type? Same type means that we might change the Q to some power of Q, but the same kind of relation. In this case, the yx will equal to Q to the power n times xy. So these two questions are very similar, I mean, in the same kind, because in the second case, the skew field with the scalar Q to the power n may not isomorphic to the original one, but they are in the same type, same kind of the skew field. So these are two open questions. Many people has studied these two open questions. Now, let's think about this. It is even not immediately clear why these two skew fields are non-isomorphic. Now, obviously, starting from the beginning, if we only look at the Bow algebra and the skew polynomial, these are non-isomorphic because
Amigo kestisem, social medindo qua, tu custais nessa moia.
Any question? Sorry. I heard some noise, some voice.
Yeah, I think someone had unmuted themselves, but you can continue, please.
Okay, all right. Yeah. Oh, yeah. If you have any questions, maybe you can put in the chat or someone can stop me do something. So I'm happy to answer any questions. Thank you. Thank you, Max Matt. All right. So now if we go back to algebra, A1, the vowel algebra is simple. The skew polynomial is not simple, so these two are not isomorphic. But after we localization, it's not really immediately clear why these two are non-isomorphic as algebras. But we will see soon that these two are non-isomorphic. Okay. So there's some partial results. I'm not going to mention the partial results. There's a group of people studying or interested in these two questions. And these are still open questions up to now. Okay. So I think there's so how to study these questions? Mike Harding gave us some idea. He said, let's use valuation. Okay, so now let me recall the definition of a valuation. The valuation was introduced in 1930s, then in the commutative side and in the non-commutative side. And obviously in the number theory, algebra geometry, I mean, this is very useful tool. And I would also like to say that this is very useful to in the non-commutative algebra. So here's the definition. So starting, let's say we have a skew field, or even a commutative field if we want. Then a map from A to Z is called a discrete valuation, or simply valuation, if we have the following 4 or 3 conditions. One is that we set value of 0 is infinity. Then this valuation map is a group homomorphism, kind of group homomorphism, sending the non-zero elements in A to the group C. This is the second one. The third one, if we take the addition of 2 elements, then this is bigger than the minimum of the value of A and B. So all of these are coming from the periodic valuation of the integer Z. So there's a lot of study in the number theory. Sometimes we want this map to be a surjective map. to avoid the trivial one. The trivial one is just setting A to 0 for every non-zero element. So we don't want to consider the trivial valuation. Now, the discrete means that the Z is like a discrete group. We can consider other ordered group. So there's other definition of valuation. But for today, we only consider discrete valuation. So I'm going to ignore the words discrete. I just call it valuation. So now why this is a useful tool to study the previous two questions. So here's a conjecture by Michael Artin. And in 1995, Michael Artin gave a lecture on this topic. And he said the following is a complete list of division algebras of transcending degree 2. So the first class is a large class. It's the division algebras satisfying a polynomial identity. So there are lots of division algebras satisfy polynomial identity. Then otherwise, then he says there's only 5 more. 5 division algebras, 5 classes of division algebras that are not satisfying the polynomial identity. So the first class is called Q rational division algebras. Q is for the quantum. So rational means like it's a field of rational functions. This is what I mean. So the first one is the one we defined in the second question. These algebras coming from the skew polynomial ring. So this is a Q skew field. The second one is a val skew field, which in the first question we talk about. Then the third one is Scalarian division algebra. I'm going to define or mention later, but this is kind of slightly more complicated. Then another class is Q root division algebras. It's kind of from the elliptic curve. There's some infinite order automorphism of the elliptic curve. Then we take our extension, take the fraction field. Then there's also the differential operator rings of the curve of high genus. So he said, okay, so these are all the complete list of non-commutative division algebras of transcending degree 2. So this Artin's conjecture is still open. I mean, almost 30 years, it's still open. If this conjecture is solved, then we can solve the previous 2 open questions. Because if this is a complete list, then if we go back to the previous questions, then we can show that these division algebras must be of that form. Okay. So the open question I mentioned at the beginning, these are kind of the subset or a sub-question of this Artin's conjecture. Any questions? Okay, so let's move on. So now, as I said at the beginning, it's not even clear why the val skew field and the Q skew field, these are non-isomorphic. There's several different proofs, but one really nice proof is by Michael Artin. And he said, let's compute the discrete valuation of these skew fields. So so for the val field, he constructs uncountably many discrete valuations, and he showed that the number of variations is uncountably many. For the Q skew field, he proved that there's infinite, but it's only countable many valuations. So from these numbers, we can see right away the val field is not isomorphic to Q skew field. Okay. Then he also did the computing for other classes, like for the or extension of the elliptic curve case, he computed the 2 discrete valuation. And for the scalar skew field, there's only 1 valuation. Okay. And he didn't do for the PI case because there's too many division algebra in that class. So, but still, if we look at the last column, the number of discrete valuations, we see immediately that the first 4 classes, these are non-isomorphic skew fields because they have a different kind of invariance. I mean, uncountable many, countable many, 2, 1, these are different numbers. Obviously, the number of discrete valuations, these are invariant of the algebra. So immediately, these 4 are non-isomorphic skew fields. This is really nice. Very nice. I mean, other proofs is very, very complicated. But this proof is the best proof. Okay. Now, so back to Arding's conjecture. He said that this is a complete list. And after 30 years, I mean, it's 1995, his lectures on 1995. So in a few days, we will be in 2025. So it's like exactly 30 years. We don't even know. We don't even have any clue if the conjecture is true or not. We cannot find any counterexample. We cannot prove this is a complete list. So, but in his original paper, he showed that the valuation is a very useful tool for studying these class of division algebras. All right. So now we move on to the Poisson side. A Poisson algebra is a commutative algebra together with a Lie bracket that satisfies the Leibniz rule. So in some sense, Poisson algebra is equal to commutative algebra plus Lie structure. If we use operatic language, the Poisson operator is a commutative operator, Y circle with the Lie operator. Then in this talk, we want to consider Poisson algebra as an infinitesimally non-commutative algebra. So it is a commutative algebra, but it is a non-commutative structure, which is Lie structure there. So we want to consider the Lie structure as infinitesimally non-commutative structure there. So this is the idea. There's a strong connection between the Poisson algebra or Poisson geometry and the non-commutative algebra and non-commutative geometry, kind of all coming from the commutative algebra geometry. Given a Poisson algebra, we can take the deformation quantization, then we get a non-commutative algebra. If we start with a non-commutative algebra in certain good cases, if we take a semi-classical limit, then we'll get Poisson algebra. So we have this triangle to connecting these 3 subjects. If we go back to the Arding's conjecture, Arding's conjecture is on the division algebra, division ring algebra, transcending degree 2. And his idea is coming from the birational geometry of surfaces. And then we feel that there should be a Poisson version of Arding's conjecture on the Poisson side. So in the Poisson side, we also should consider the Poisson field of transcending degree 2. Then hopefully, if we understand the Poisson side, then we have some idea on the non-commutative algebra side. So just keep this in mind. If we have a Poisson field, we should have a division, skew field on division side, meet. The same is not true actually, but hopefully for certain cases, a Poisson field with a transition degree 2 will give us a skew field of a transition degree 2. If we start from the skew field of transition degree 2, if we take a semi-classical limit, we should get a Poisson field of transition degree 2. That's the idea, keep in mind. Okay, so let me give you some examples of the Poisson algebra or Poisson field. So as I said, the Poisson algebra is a commutative algebra with Poisson bracket. So if we start with the commutative polynomial ring kxy with a Poisson bracket determined by the bracket x with y equal to h of xy. And then you can check that this extends to the whole algebra. So this is a Poisson algebra. And this is called skew Poisson polynomial ring. The corresponding non-commutative algebra is the skew polynomial algebra, which is given in the question number 1 at the beginning of this talk. So if we go back, now we are in this side, the Poisson side. I give you example of Poisson algebra, the Poisson bracket. It's a commutative polynomial ring with Poisson bracket determined by bracket of xy equal to h of xy. I claim that this, if we take deformation quantization, you get the skew polynomial ring. Starting from the skew polynomial ring, if you take semi-classical limit, you get this Poisson algebra. So the corresponding non-commutative algebra is the Q skew polynomial ring. So this is the first example of the Poisson algebra. And of course, everybody knows this. The second example, if we change the Poisson bracket xy equal to 1, then this one is called the val Poisson polynomial ring or algebra. And basically for any f and g in the polynomial ring, and the Poisson bracket is given by this formula. Then the corresponding non-commutative algebra is the first val algebra. Okay, so these are the first two examples, kind of corresponding to the first two open questions at the beginning of this talk. Now we can have Poisson version of the two open questions. So remember that I start with the example 1 is a skew polynomial, Q skew polynomial. The second one is a val Poisson polynomial. But then I switched. The first one is a val Poisson field, which is the fraction field of the val Poisson polynomial ring. I use K val for this Poisson val field. So the Poisson version of the first question, open question is that, is every Poisson subfield of this Poisson field of transition 2 isomorphic to itself, the K val, which is Poisson val field. So this is very much like the first open question. Then the second, the Poisson version of the second question is that if we take the KQ, Q is a non-zero scalar, to be the Poisson field determined by the example 1, then the question is every Poisson subfield of transition degree 2 isomorphic to K of n times Q, not Q to the power, but the multiple of n to Q for some integer. Okay, so these two are the Poisson version of the open question 1 and open question 2. And all these, these Poisson versions are still open. But somehow we feel that the Poisson version are slightly easier to work with. But I don't know. These are still open, so maybe equally difficult. Equally difficult. Okay. So now the first question for the Poisson version of the Val Poisson field is statement is kind of exactly the same, right? The subfield should be isomorphic to itself. But for the second one, there is a small change. Originally, we can go back. Let's just go back. Oops. Originally, we say any skew field of KQ is isomorphic to K of Q to the power N. This is the non-commutative version. But in the Poisson version, we have any subfield of KQ is isomorphic to K of NQ. So the Poisson version is kind of linearization of this non-associative version. Okay. All right. So let me see if there are any questions. Okay. Good. So now we can have more examples. This is related to scalar algebra. We take a polynomial of 3 variables. The Poisson bracket determined by these. These are Poisson bracket on the generators. So you can extend this to the whole algebra. This is called the elliptic or Poisson scalar or elliptic Poisson polynomial algebra. The corresponding non-commutative algebra is 3-dimensional scalar algebra, which is generated by X, Y, Z subject to the 3 relations. So just keep in mind that if we have a Poisson algebra, and there should be a non-commutative algebra, and vice versa. Non-commutative algebra, maybe there should be a Poisson algebra there. So to understand the scalar algebra or elliptic algebra, maybe it's a good idea to first understand the corresponding Poisson algebra. We can extend this example to high degree version. We let omega be element in polynomial ring of 3 variables. Then we can define the Poisson bracket determined by these. So in the previous example, we just take omega to be this element. And in general, omega can be any element. So this will be a Poisson algebra. And if the Poisson algebra is defined by this omega, then this will be a unimodular Poisson algebra. And if omega is homogeneous, then this Poisson algebra is also homogeneous. Okay. So starting from this omega, sometimes we call omega the potential of the algebra. Then omega will be in the Poisson center, which means that the bracket omega with any other element will be 0. So since omega is in the Poisson center, then we can mod out ideal generated by omega minus any scalar psi. Then if this element is irreducible, then since this is this polynomial ring is UFD, so this mod out this will be a domain, so we can take the fraction field. So we can construct different Poisson field starting from this. Now, if we choose omega carefully, so this is a domain. This ideal P of omega minus psi is domain of GK dimension to transcending 2. So the fraction field, it will be a field of transcending 2. So these are kind of nice examples. So as I said at the beginning, Mike Arting taught us that we should use valuation to study division algebras. So for Poisson field, we also might use valuation to study these Poisson field. So here's the definition of valuation for the Poisson algebra. So the first three conditions are the same, just the usual definition of valuation. So if we start with a Poisson algebra or Poisson field over a base field K, now for the Poisson case, we introduce another parameter omega or W is a fixed integer. Then a Poisson mu is called a Poisson valuation, W valuation if we have these four conditions. The first three conditions just the usual valuation axioms. The last one involves the Poisson bracket. So the last one, this one is involved the Poisson bracket. Since the valuation is algebraic invariant, so we can have a action of the Poisson algebra automorphism to all the W valuations. So we have this action. So most of the proof of the later results will be based on this fact. Okay, so basically how do we imagine the Poisson valuation? It's a valuation, but it's compatible with the Poisson bracket. So the new one, if we take omega W to be 0, this is a very natural axiom for Poisson algebra. First three are the same, just the usual valuation axiom. The last one involved the Poisson one. And the extra parameter kind of give us some extra information. So we will keep that. Now, starting from valuations, then we can define sort of the alpha invariant, beta invariant, gamma invariant, all different kind of invariant. All these are in our paper. So if you're interested in to know these, you can look at our paper. Then, for example, for the gamma invariant, we can define more from that. So there's lots of numbers, sets, and properties coming from these Poisson valuations. And the gamma invariant has been used to study automorphism group, for example. So we'll talk about automorphism group a little bit later. Okay, so now remember that in Arting's conjecture, he said that we have this class of division algebras, and he computed the number of valuations, number of the classical valuations for four classes, four families of the division algebras. So now we want to do this for the Poisson field. And if we start with the val Poisson polynomial ring, if we take the fraction field, then we compute it. There's uncountably many zero valuations. I mean, in this page, we only talk about zero valuations, but we can also talk about other W. But for zero valuations, there's uncountably many for the val Poisson field. For the skew Poisson field, we compute it. There's only countably many zero valuations. For Schillerian Poisson polynomial ring, and then we take the quotient, then there's only one zero valuation. And for the graded version of the Poisson scalar type, there's 2 zero valuations. And if we take some potential omega, which has isolated singularity at origin, and the degree is at least 5, then we prove that this has no zero valuation. Okay, so maybe there's too much information, but let's see a table for this. So it's a kind of comparison between the Poisson field and division rings. In the second column, the first 4 cases, this is did by Michael Artin. Okay, and now for the Poisson field of transitivity 2, for the Weil field, we computed uncountably many discrete variations. For the Q-skew Poisson field, we computed countably many. For the graded version of elliptic case, and we computed 2. And for the scalar Poisson one, we computed 1. Now, the reason we put these 2 columns together, because these are exactly what Mike Artin found out in like 30 years ago for the division algebras. The last column, if we take omega have degree at least 5, then we cannot find a division algebra of transitivity 2 corresponding to that Poisson field. So our conjecture is that this has transitivity bigger than 2. Then we computed the discrete valuations, no zero discrete variation. So in the last case, when we take deformation quantization, then the algebra, the transitivity of this algebra is bigger than 2. So this will not be in the list of Mike Artin's conjecture in this case. All right, so this is a comparison. This is exactly same. Of course, the way we compute it is different, but the results are exactly the same. So this also suggests that there's a really tight connection between the Poisson side and the non-commutative side. Okay, so for the rest of my talk, I'm going to mention a few applications of the valuation. There are lots of applications, but probably I only have time to talk 1 or 2 today. So maybe I will mention number 1, automorphism problem, number 2, isomorphism problem, number 6, a Dix-Meer problem. I'm not going to talk about other applications. All right, so automorphism problem basically is to compute automorphism group of some object. So this is always a very interesting topic for any subject of mathematics. Here we're going to compute automorphism group of some Poisson field. And as we know, automorphism of the field of transitivity 2, usually it's huge. I mean, like polynomial of 2 variables are huge. But automorphism, we will see the automorphism of a certain Poisson field could be small. So for the rest of talk, we will take a potential omega to be a homogeneous element in polynomial XYZ of degree at least 5. For degree 4 and lower, the theorem will be different. It's kind of more complicated. But for degree 5, we have some nice results. So assume that omega has isolated singularity at origin. Then the KXYZ omega, this is Poisson polynomial algebra giving in the example 4. Maybe we can go back to take a quick look what is Poisson polynomial in example 4. It's a Poisson, first of all, it's a commutative polynomial in XYZ. The Poisson bracket is determined by these. These are the generators, but you can extend this to any function in the polynomial of XYZ. Okay, so this is the example we are focusing on. Okay, so this polynomial ring of 3 variables, it has transcending degree 3. Then if we take the fraction field, this also has transcending degree 3. So the question is that what is the automorphism group of either this polynomial, Poisson polynomial ring or the Poisson field? So we're going to answer this question. So remember that omega is a potential, has isolated singularity as origin, and has degree at least 5. That's our hypothesis. So here's one main result. First, the automorphism as algebra, the Poisson automorphism of Poisson field is equal to the automorphism of Poisson algebra. Okay. Second, we have explicit kind of description of this automorphism group, which is a finite subgroup of this GL3 of order bounded by above by this number, okay, where D is a degree of omega. So I say if D is 5, then this will be 5. But the result works for any D bigger than or equal to 5. So we have a bound, and actually we have some kind of short sequence to give more structures. So for example, if we take omega to be just this formal polynomial x d, y d, and z d for d bigger than or equal to 5, we always need this hypothesis. Then there is an exact sequence. So this is a automorphism group, and this is a group of order d minus 3. This group of d order d times d minus 3. This is a Abelian group, and this is a symmetric group. So we have a short exact sequence of this form. And by the first part of the theorem, the automorphism group of the field, the Poisson field, will equal to this. So we can replace this by the automorphism group of the field if we want, because they are equal. Right. So this is about automorphism group. So here, I just give an example. I mean, we can do something with using valuation. Now, of course, I'm not going to give you any proof, but this one idea that the Poisson automorphism acts on the valuations. So if we can have control on the valuations, then basically we can say something about the automorphism group. So that's one basic idea. All right. So let me see if I have time to. Yeah, okay. So let me also mention some results concerning the Dixmude property. So here's the definition. What is Dixmude property? If A is algebra, we say A has a Dixmude property if every injective endomorphism of A is bijective. Okay. Now, we know that every finite dimensional algebra has a Dixmude property, because if injective by dimension count, it must be surjective. Then the Val Poisson field, or the skew Poisson field, or the Val field, or the skew field, they do not satisfy this Dixmude property. The Val field or Val Poisson field, these are infinite dimensional, and we can construct easily the injective endomorphism, which is not bijective. On the other hand, Dixmude conjecture says that the nth Val algebra has a Dixmuir property. So this is called the Dixmuir conjecture, which is stably equivalent to the Jacobi conjecture. Another conjecture related to this is called the Poisson conjecture, which says that N's Poisson Wahl algebra has a Dixmuir property. And basically, these three conjectures are all stably equivalent. So Dixmuir property is coming from the Dixmuir conjecture, basically. Okay, so Dixmuir property, if we can handle the Dixmuir property for the Wahl, N's Wahl algebra, then the Dixmuir conjecture is solved. All right. So now we understand the definition of Dixmuir property. And we know that finite dimensional algebra, any finite dimensional algebra, is the algebra, Poisson algebra, associative algebra, any algebra. If finite dimensional just has Dixmuir property. But infinite dimensional ones, usually we don't have Dixmuir property. Okay, so now I want to give some example of Dixmuir property. So basically, we want to say, what is there a criteria for the Dixmuir property? One result in the Poisson side is the following. If we take the potential omega, which has isolated singularity and the degree is at least 5, then this polynomial Poisson polynomial ring defined by the omega, this has Dixmuir property. Same for the field. Poisson field that has a Dixmuir property. Okay. Now these are the algebra we define this K, X, Y, Z, omega, and this is not the Poisson Wahl algebra. Okay, so we didn't solve the Poisson conjecture. We just say for a certain class of Poisson polynomial rings, we know this has Dixmuir property. All right. Let me see. I have 2 minutes. Okay. Great. So let me mention quickly about the isomorphism problem. So isomorphism problem, again, it's very general problem in mathematics, which is determining whether two objects in the same family are isomorphic or equivalent. So remember when I say, remember at the beginning of the talk, I said the Wahl skew field and the Q skew field, it's not even clear why these two are not isomorphic. So this is kind of isomorphism problem. And by Arding's computation, they have a different number of valuations. So we know they are non-isomorphic. Okay. So isomorphism problem is to determine whether two objects are isomorphic or equivalent. So now, given two Poisson fields, how can we determine if these are isomorphic or not? And then one idea is Arding's idea. We can compute the valuation. If they have different number of valuations, then they are not isomorphic. But then, even if they have same number of valuations, we can use some other invariant to decide if they are isomorphic or not. So here's one case. Sorry, this is I'm already out of time. But maybe let me just
don't worry, we started a couple of minutes late, so don't worry, you can finish what you're explaining.
Okay, thank you. So I will finish in 2 minutes then. Thank you very much. So the question is, if we have two Poisson algebras, two Poisson field, which is defined by the first line here, how can we say, for determining whether these two are isomorphic by using the property of B and the B prime? Okay, so here is some examples. If we take any polynomial ring, a polynomial of X in this algebra, we have x, y. If we take x, it's always isomorphic to the vowel Poisson field. But if you take this element, this will isomorph to this. So it's not clear what is the criteria. But somehow we figured out one case. If we have x, gx and hx, two polynomial of positive degree, then k of this Poisson field isomorphic to k of this kind of Poisson field, if and only if this g and h satisfying this equation. So that's one application of the valuation. Okay, I stop here. Thank you very much.
Well, thank you very much, James, for this very nice and very interesting talk. So before leaving some time for people maybe asking a question, I have a quick one. So can you explain maybe why in the previous two problems the degree of the potential should be greater or equal to 5? Is there a reason why for a lower degree it's failing?
Yes. So for degree less than or equal to 2, there will be a lot of valuations, so we cannot handle that. For degree 3, we need to use like W valuations. There's some complication there. For degree 4, then we need to like -1 valuation, which we cannot handle in some special case. But for degree 5, suddenly for -1 valuation, we can handle everything. So that is a reason there.
Mm-hmm.
But yeah, so something failed for degree strictly less than 5.
Mm-hmm. Oh, okay, that's very nice.
Yeah,
that's
but I
very
didn't say why, but yeah, that's the reason. Yeah.
Are there any questions from people in the audience? Okay, well, if not, it's been a very long day. So thank you again, James, for this very nice talk. And let's also thank the different participants, speakers, and obviously the organizers for this extremely nice day that we've had today. So thank you very much to everybody.
Thank you.